All right, hello and welcome. Have you ever really stopped to think about the humble straight line? I mean, they're literally everywhere, right? The roads we drive on, the charts we see on the news, even the buildings all around us. But what if I told you they hold a secret language? A language that lets us describe our world in this incredibly powerful way. Well, today, we're going to decode that language. And believe it or not, it all kicks off with a really simple question.
And that question is this: how can a simple board game, one you've probably played 100 times, unlock the secrets of everything from your phone build to a cross-country race? Stick with me here, because the answer is way simpler and honestly more beautiful than you might think.
So our whole journey starts with something we all face, the problem of place. Where is something? And there's no better way to get our heads around this than by playing a little game of Battleship.
Okay, so what's the absolute #1 rule of this game? It's being able to call out a single square with perfect pinpoint accuracy. You can't just vaguely say, that one over there. No way. You need a system, a shared language, so that when you shout B5, your opponent knows exactly which square you mean. Whether it's a hit or a miss, it all boils down to one simple thing: location.
So that system, it actually has a name, and it's called Cartesian coordinates. Sounds fancy, but the idea is super simple. It just means that any point on a flat surface, any point at all, can be nailed down with just a pair of numbers. The first number, x, tells you how far to go across. The second number, y, tells you how far to go up or down. That's it. It's like the universal code for, well, you are here.
Okay, so now we can pinpoint any single spot. That's great. But what happens when the points aren't just random dots all over the place? What if they start to follow a rule? This, my friends, is where it all gets really, really interesting.
We call this rule a function. Now that word sounds a bit technical, I know, but it's a really simple idea. A function is just a consistent, predictable relationship. For every input you put in, you get one specific output back. So think about buying some tea. The amount of tea you want to buy is your input, and the total cost, that's your predictable output.
And this is a brilliant way to see the difference a rule makes. Look on the right, we're buying tea bags. You can only buy whole boxes, right? So you get these separate, lonely little points for the cost. But now look at the left. Here we're buying loose leaf tea. You can buy any amount you want, a tiny pinch, a whole kilogram, whatever. And because of that, the points all connect, and what do they form? A perfect, continuous, straight line. That single line holds the cost for every single possible amount of tea you could ever want to buy.
All right, now that we know how to make these lines, how do we talk about them? Let's start with the most obvious thing you notice: their steepness. Just how sharp is that angle?
Let's make this super intuitive. Just look at these two paths. You don't need a single bit of math to know that walking up slope B is going to be a much tougher workout than walking up slope A. It's just steeper. We all have this natural built-in feeling for it.
Well, in math, we have a specific word for that feeling of steepness. We call it gradient. And it's not just some vague idea. It is a single, hard number that tells us exactly how steep any line is. No guesswork. And the direction of the slope tells a story too. If a line is going up as you read it from left to right, like you're climbing a hill, it has a positive gradient. If it's going down, like you're skiing, it has a negative gradient. It's really as simple as that.
Okay, so let's get practical. Take a look at this line. We can see it's going up, so it's a positive gradient. But how steep is it? Exactly. How do we find that one single number, that gradient?
The formula for it is just beautiful in its simplicity. The gradient is just the vertical change divided by the horizontal change. You've probably heard this called rise over run. It's just a simple ratio. For every step we take across, how many steps do we take up?
Let's try it on our line right here. If we pick any 2 points on it, we can see that to get from one to the other, we have to move 2 steps across to the right. That's our run. And in that same move, we go 6 steps straight up. That's our rise. So now we just do the math. Rise divided by run. 6 divided by 2 gives us a perfect, precise number for the gradient. It's exactly 3.
So, we've got the pieces now. We can find any location on a grid, and we can calculate the steepness between points. It's time. Let's put it all together and finally reveal the secret formula that can describe any straight line in the entire universe. But first, really quickly, 2 special cases. A totally flat horizontal line has 0 rise, right? So its gradient is just 0. A perfectly straight up and down vertical line, well, that has 0 run, and you can't divide by 0 in math, so we say its gradient is undefined.
You could almost think of it as being infinitely steep.
And here it is, the secret code we've been building up to. Get this, y equals mx plus c. That's it. That tiny equation is all you'll ever need. We already know m, right? That's our gradient, the steepness we just figured out. And c? Well, c is just the y-intercept. It's simply the starting point, where the line hits that vertical axis. So think about it. With just two little numbers, m and c, you can now describe any straight line. How cool is that?
So, what's the big deal? Why does any of this matter? Well, this is the payoff. Let's take a look at how this secret language of lines helps us understand and deal with the real world all around us.
Have you ever taken a taxi? The way they calculate the fare is a perfect straight line. There's that fixed starting charge just for getting in. That's your C, your y-intercept, and then there's a set cost for every single kilometer you travel. And that's your M, the gradient. It's a perfect real-world example.
Or what about a cyclist's journey? If you plot their distance against time, the gradient of that line is their speed. A really steep line means they're going super fast. And what about a totally flat horizontal part? Well, the gradient is 0, which means their speed is 0. They've stopped for a break.
Oh, this one's my favorite. Comparing two different phone plans. You can draw each plan as its own straight line. And you see that point where the two lines cross? That is the exact moment, the precise number of minutes where one plan becomes a better deal than the other one. This is literally math helping you save money.
Okay, time for one last challenge for you. Here, we've got a graph that shows a race between two people, Imran and Shufen. They're traveling from a place called Greenfield to another called Red Hill. Now, it might look a little complicated, but really, it's just a story being told with a few straight lines.
So I'll leave you with this question. Looking at this graph, who wins the race? Who makes it to Red Hill first? You now have all the tools you need to figure it out. The answer isn't in some book. It's right there, hidden in the secret language of the lines.